In this video, we're going to look at an example where we're given two vectors and we're asked to produce a vector that is orthogonal to them. So here's the example. We have these vectors p1 and p2, and we want to find a vector p3 that is orthogonal to both of them, to both p1 and to p2. Okay, so there's an easy answer to this. There's an easy answer that we could tell without even doing any computation. I'd encourage you guys to pause the video for about 30 seconds and think about what is that easy answer, something that's perpendicular, orthogonal to both of these. So 4, 3, 2, 1, pause the video for about 30 seconds and think about that. Alright, so hopefully you guys did that. Hopefully you guys paused the video for about 30 seconds and thought about it. So the easy answer is, well, we could let P3, let's keep this in blue actually, we could let P3 be the zero vector, because the zero vector is orthogonal to everything. If we dot the zero vector with anything, we'll get 0. Okay, so the more interesting question is, well, how do we get a non-zero P3? Because that's certainly something that we could be asked to do. So if you've taken multivariable calculus before, you might remember something called the cross product to generate perpendicular vectors. But in Math 54, we don't have a cross product. There is no cross product. There is no cross product for us to use. Okay, so if we let ourselves use the cross product, that would certainly be a way to do this. But let's try to do this just using linear algebra techniques, so no cross products. Okay, so I'm going to talk about how to do this in two ways. So the first way is, well, let's just begin by letting P3 be a vector with entries A, B, and C. And let's try to figure out what these are. So what we know about P3 is, we want P3 to be, let me put an arrow on top of it for vector arrow. We want it to be orthogonal to P1 and to P2. So these dot products should be 0. Whoops, let me fix this. This shouldn't have a vector on it, because after we take a dot product, it should be a scalar. Okay, so let's work out what these dot products are. So if we dot P1 with P3, so P1 is the vector 2, 3, 6. So we want to dot that with P3. P3 is A, B, C, and we need this to be equal to 0. So when we dot these, if I take the inner product of these, we'll get 2A plus 3B plus 6C equals 0. So we get this equation. Now, let's do P2 dotted with P3. So P2 is the vector 0, 2, negative 1. And let's dot that with P3. So P3 is this A, B, C vector. And I want this to equal 0. So if we take the inner product of these, in other words, if we take the dot product of these, we'll get 0A plus 2B minus 1C, and that should be equal to 0. Alright, so what we have now is we have these two equations. In other words, we have a system of equations. And I've actually gone ahead and written that down already. So we have this system of equations that we need to solve. But we've been doing this throughout the course, as early as chapter 1, solving systems of equations. So we could set up a matrix for this. So we'd get 2, 3, 6 for the first row, augmented with 0, if we want to set up an augmented matrix for this. And then for the next row, we'd get 0, 2, negative 1, augmented with 0. Because this is a homogeneous system, if I wanted to set up just the coefficient matrix and then work with that, we could. Okay, so let's row reduce this. So let's row reduce so we can figure out what the solution is to this system. Alright, so what I'm going to do first is I'm going to multiply the second row by 1/2 to turn that pivot into a 1 and insert this into the second row. So the first row stays the same as 2, 3, 6 augmented with 0, but the second row gets divided by 2. So I get 0, 1, negative 1/2, 0. Alright, now let's do another row operation. Now I'm going to try to zero out this 3. So I'll do a negative 3 times row 2 and add that to row 1. Insert into row 1. So that'll give us, second row stays the same, 0, 1, negative 1/2, augmented with 0. But the first row will become 2, 0. So that part is the part that should be quick to see. So if I multiply negative 3 times negative 1/2, I'll get positive 3/2. And notice that 6, well, 6 is the same thing as 12/2. So 12/2 added to 3/2, that's going to be 15/2. That is going to be 15/2. Okay, and this is still going to be a 0 over here. All right. So you may have noticed that I changed the colors on 2 of these rows. And the reason I did that is so that they matched up with the colors that I had for these vectors over here. And I wanted to do that because when I talk about how to do this with the second method, I really want to highlight the role that these rows are playing here and these column vectors are playing. All right, so next let's continue to rows. So let's row reduce some more. So let's divide the first row by 2. So 1/2 row 1 and insert into row 1. And that'll give us 1, 0, whoops, sorry, not negative, positive 15 over 4, augmented with 0. And the second row stays the same as 0, 1, negative 1/2, augmented with 0. Now we have this in reduced form, so we could write down the equation for each row. So I'll get x1 plus 15 over 4, x3 equals 0. And from the next row, I get x2 minus 1/2, x3 equals 0. So now let's isolate the pivot variables. So doing that, we'll get x1 equals negative 15 over 4, x3, and x2 equals 1/2 x3. All right, so now we're ready to write down our answer as a vector. So x is a vector, we'll have x1, x2, and x3. And plugging in for these, I know what x1 is. It's negative 15 over 4, x3. x2 is 1/2 x3, and then x3 was free, so we leave that how it is. So x3, leave it how it is. Oops. Let's fix that. Okay, and now I can factor out the x3, the free variable, and be left with negative 15 over 4, 1/2, and 1. So at this point, we know what the solution set to this equation is going to look like. Any vector that has this form should be perpendicular to P1 and P2. But our problem said, well, just pick one. Just find one vector. So we can set x3 to be whatever we want. So it's going to be nice if we pick something that'll get rid of these fractions. So I'm going to pick x3 to be 4. And if I do that, then my vector P3, so if I multiply all of these by 4, we'll get negative 15, 2, and 4. So this is one vector that is going to be orthogonal to both P1 and P2. So if we were to check this, we would want to make sure that P1 inner product with P2 is 0. And if you do check it, you'll get that this is the case. And it also turns out that if you take the inner product of, oops, sorry, I think I meant to write P3 there. Sorry, P1 inner product with P3. And then also P2 inner product with P3 should be equal to 0. Right, because I want P3 to be orthogonal to both P1 and P2. So I'd encourage you to check this. Like, go back to the top of the problem and take the inner product of P3 with our vectors P1 and P2. So next, I want to do this in another way. So this next method, it turns out, is equivalent to the first thing that we just did, but it's a little bit more compact in terms of notation, and that lets it generalize nicely to if we wanted to do this with more vectors, if we're working in higher dimensions. So what I will do is, I'm going to define a matrix A, in which I put P1 and P2, these are the given vectors, as the columns. So I've gone ahead and done that. So these were the two vectors, P1 and P2, written as the columns. So next I'm going to think about the column space of this matrix. So the column space is the span of the columns. So the first column is 2, 3, 6. The next column is 0, 2, -1. So let's think about this column space. So what it is that I want is we want a vector that is orthogonal to these two columns. Well, what if we could just get a set of vectors that is orthogonal to the entire column space? Because if I can get that, if I can get some vectors that are orthogonal to the entire column space, well then they'll definitely be orthogonal to the columns themselves. Okay, so i.e. in other words, well, what do we call the set of vectors that's orthogonal to this subspace? Well, that's the orthogonal complement of the subspace. And the notation for that is we write the subspace, in this case it's the column space, and we put this perpendicular symbol up here. So that refers to the orthogonal complement. And all that means is, well, this is the set of vectors that is orthogonal to our subspace, in this case to the column space of A. So in the last video, oops, I don't want to get carried away too far. In the last video, we stated a theorem about what the orthogonal complement of the column space of A is. And we said that the column space of A's orthogonal complement is the null space of A transpose. So because I'm trying to find some vectors that are orthogonal to the column space, what this theorem says is, well, if I want to do that, just find the null space of A transpose. So if we transpose our matrix, so here's A, if we transpose this, we get the matrix 2, 3, 6 as the first row, 0, 2, -1 as the second row. And this is actually the same matrix that we had in method 1. So if I zoom out a little bit, to method 1, we had this same matrix here. We had that same matrix. That's why these two methods are actually equivalent. And we row reduced this fully. So if I zoom it back in, I've just gone ahead and said what the final row reduction was. Okay, so what I want is, well, I want to know what a basis for this null space is going to be. A basis for the null space of A transpose. So just like before, how we got in method 1, it turns out a basis for this null space is going to be -15, 2, and 4. And that was actually something that we worked at in method 1, so it's the exact same computation for how we get this basis. So notice that it's the same thing in both of these methods. But like I mentioned before, method 2 is nice because it involves some more compact notation, and it'll generalize nicely when I have more vectors and I'm working in higher dimensions.